All right, so we're done with chapter 4. So chapter 5 gets a bit different because it's going to be a lot of quantitative type of things that we're doing now. So the whole first 4 chapters were mostly conceptual, and now we're going to start talking about more macroscopic chemical properties. So chemical properties that involve huge ensembles of atoms and molecules as opposed to individual atoms and molecules like we've talked about up until now. Okay, so the first thing we're going to talk about is atomic mass, and we kind of already have an idea of this based on some things we've talked about, but there's some more details we need to get into now. So atomic masses can be measured in what are called atomic mass units, and this is going to be essentially the mass of a single atom, if we want to think about it that way. So now an AMU is defined as the mass of 12 carbon divided by 12. All right, so it's 1/12 the mass of 12C. So we know that the mass number for this isotope is exactly 12, and if we divide that by 12, we'll say that one mass unit is exactly equal to 1/12 of that. So this carbon-12 is the standard, and so all other atomic masses are measured relative to this. I'm not sure why this one was chosen as a standard, but it's a very abundant, very stable element, I suppose. So they chose this as the standard and measured all other atomic masses relative to this. Now that's a detail that's not terribly important for us, but that's where these atomic masses come from. So as an example, if we were to take, and one of the reasons for this is that experimentally, there's not really a good way to measure the absolute mass of something, especially if it's something that small, but you can measure relative masses pretty easily. So if you can measure the relative mass and then set it relative to some standard, then you can define all atomic masses on a consistent scale. So, for example, if we took 13C, which just has one more neutron in the nucleus, and we took the ratio of those two masses, it comes out to 1.0836. And so then if we multiply by 12 to get the mass of 13C, so in other words, the mass of 12C is exactly 12 AMUs, so the mass of 13C is going to be 1.0836 times that, which is pretty close to 13, but not exactly 13 AMUs. So the question may be arising, well, why isn't the atomic mass exactly equal to the mass number? We said the mass number is the number of protons and neutrons. There's 2 reasons for that. So one is that protons and neutrons don't have exactly the same mass. So even if you set the mass of a proton or a neutron to 1 AMU, they're not going to be exactly the same, so you wouldn't have exactly a whole mass number, or atomic mass in every case. But the bigger thing is that, and something that you'll learn a lot more about in chemistry too, is that there's this theory of general relativity, E equals mc squared. And so basically what happens is that when nuclei form, a lot of energy is released. And this equation tells us that really, as part of that quantum theory that we talked about, energy and mass are really the same thing. So when you release all this energy from forming a nucleus, you also release some of the mass. And so what this means is that nuclei are not going to be exactly equal to whole number atomic masses. In other words, let's say if we take a nucleus that has 10 protons and 10 neutrons, the atomic mass of that is not going to be exactly 20 because there's going to be some mass loss when those protons and neutrons come together. So a lot of energy is released when nuclei are formed, and this changes the mass. And we don't have to worry about this detail too much now, but you'll see it in chemistry too when you guys talk about nuclear chemistry. All right, but that's why you can't just add up the number of protons and neutrons and say that's going to be the atomic mass. There's going to be some difference because of the energy that's released when those protons and neutrons come together. So that's how we sort of get the masses of individual isotopes. It's roughly related to the number of protons and neutrons, with some difference because of E equals mc squared. But then what we're more interested in is what's the atomic mass of a natural sample of an element. So if we just were to go out back and collect soil and extract all the iron from the soil, for example, what's going to be the atomic mass of that iron, which is a mixture of isotopes. So if we want to report the atomic mass of a naturally abundant element, we use what's called the percent abundance. And this is the relative amount of each isotope in a natural sample of that element. So if we go back to the example of carbon, carbon has two naturally occurring isotopes. The major one is 12, carbon 12, that standard one that we talked about, which is 98.89% abundant. So the vast majority of carbon is carbon 12, but there's also the rest, a little bit, is going to be 13 carbon, which has about a 1% abundance. So if you were to take a sample of pure carbon that's naturally occurring, it's going to have almost 99% 12 carbon, and then it's going to be 1% 13 carbon. So how do we report the atomic mass of that when it has two different isotopes present in it with two different masses? And so that's where we sort of get this definition for atomic mass, the one that we're going to report and the one that we're going to use when we do calculations. And it's going to be the weighted average of all of the isotope masses. All right, so we use the fractional abundance of each isotope, and we multiply it by the individual isotope mass, and we add them together. So it's going to be, if we have two isotopes A and B, the fraction of isotope A times its mass, plus the fraction of isotope B times its mass, and you do that for however many isotopes you have that are naturally occurring. So most elements have more than one naturally occurring isotope. So the atomic mass that you see, which is going to be the mass that's on the periodic table for each element, is going to be reported as a weighted average of all of the isotopes that are present in that sample. There are very few elements, if any, that have only one isotope that naturally occurs. All right, so if we go and then do a sample problem with this, we have another element, boron, which consists of the isotopes 10 boron, which is, again, 10.01294 AMU, so not exactly equal to the mass number, and it has 19.9% abundance. Then we have 11 boron, which is slightly above 11 AMUs and has an abundance of just over 80%. What is the atomic mass for this? All right, so again, the atomic mass is the weighted average of the two isotope masses. So we take the fractional abundance of one isotope, 10 boron is the first one that we were given, times its mass, plus the fractional abundance of the other isotope times its mass. When we have two isotopes here, if there are more than two, you'd have to keep adding up all the terms for the rest of the isotopes, however many there are. Now remember that when we're using this equation, we have to use fractional abundance, not percent abundance. So again, it's kind of like we talked about with mass fraction and mass percent. There's two different ways of reporting it. The percentages are out of 100, but we want the fraction, which is out of 1. So the fractions are going to be the percentage, which is for 10 boron is 19.90, and then you have to divide that by 100 to convert it to a fraction. Right, if you don't do this, then your reported atomic masses are going to be 100 times too big. And then by the same argument, the fraction of 11 boron is going to be 0.8010. All right, and so again, the percentages should always add up to 100 for all the isotopes that you have. The fractions should all add up to 1 for all the isotopes you have. Those are also important relationships for some of these problems. But in this case, we're just calculating the atomic mass, so we just take that equation on top and plug in the correct number. So the fractional abundance of boron 10 is 0.1990. Its mass is given to us as 10.294. AMU. The fraction of the second isotope is 0.8010. Its mass is 11.000. 0.0931. And so when we add these up, we get 1.993 plus 8.818, 10.811 AMU. All right, so that's the atomic mass for naturally abundant boron. And remember that this is the mass that's going to be reported on the periodic table. So if we go to the periodic table of elements and find boron, boron is atomic number 5, and this number that's underneath the symbol, 10.811, that represents the natural atomic mass. The weighted average of all the isotope masses for boron is 10.811. So that's what all these numbers then mean on the periodic table that are underneath the elements. Those are the atomic masses, and they represent the weighted average of all the possible isotope masses. Because anytime you have one of these elements, in most cases it's going to be a collection of 2 or more isotopes, and when you want to use the mass of that element, you want to consider the weighted average of all those isotopes. Okay, so that's how we do it to calculate it. And then another variation on this problem is where we give you the atomic mass. So the atomic mass of chlorine is 35.45. We can see that in the periodic table. And it has 2 naturally occurring isotopes. We gave you the masses for both those isotopes, and then we want to know what is the percent abundance of 35 chlorine. So in this case, we're kind of working backwards. We gave you the atomic mass. We want you now to extract out the isotopic abundances. All right? So what we have to do then is set up a couple equations where we have some unknowns. So just to keep things simple, I'm going to call the fractional abundance of 35 chlorine, I'm going to call that X. So we really have 2 unknowns in this problem. We have the abundance of 35Cl and the abundance of 37Cl. We're only asked to solve for one of them, but we don't know either of them at the moment. So we're going to call that one X. We'll call 37Cl Y. So those are going to be our 2 variables in this problem. And then remember that we have now an equation we can write. So the atomic mass of chlorine, which is 35.45, is the weighted average of the isotope masses. So that 35.45 is going to be equal to the mass of the first isotope times its abundance. So the mass of 35 chlorine is 34.96885. And we multiply that by the abundance, which we called X. We add that to the second isotope mass, 36.96590. So remember, there's no way to calculate these isotope masses because there's that whole E equals MC squared part. So these are going to be a little bit different than the mass numbers, as I talked about at the beginning of this. But that's going to be the mass of the second one, and then its abundance we called Y. Now we have a problem here because we have one equation and 2 unknowns, and anybody who's taken algebra knows that you can't solve this. But remember that there's another relationship involving X and Y. These are the fractional abundances, and as I said in the last one, they have to add up to be 1. So we have a second equation, X plus Y equals 1. The sum of those 2 abundances has to be 1. And in this problem, we're solving for X as we defined it. So we're solving for the abundance of 35Cl, which we've called X. So we can rearrange this and say that Y is equal to 1 minus X. We take this, we substitute it into the equation. Okay? So we're just doing 2 equations, 2 unknowns, but the second one's a very simple one, X plus Y equals 1. And so now we can substitute for Y, rewrite the equation, Right, now we have a single unknown in our equation because we replace Y with 1 minus X. We're going to solve for X by doing some algebra that I'm not going to go through in detail here. And we get X is equal to 0.7590. And I remember that that's the fractional abundance. The question asked for percent abundance, so the percent abundance is going to be just 100 times that. So 0.759 times 100, which is 75.90. Okay, so that would be choice C in this multiple choice example. Alright, so there's really only one equation you have to worry about, or I guess 2 if you want to consider this relationship between the abundances. But those are 2 typical types of problems. We'll either give you the abundances and the masses and ask you to find the atomic mass, or we'll have you work backwards, where we give you the atomic mass and have you solve for either the abundances or one of the individual isotope masses. So there's a few different ways we can present these problems, and it's really all the same idea. Now, another important parameter in chemistry when we start talking about collections of atoms is going to be the mole. All right, so we've talked about sort of the individual masses of elements, their atomic masses, and now we want to see another important parameter called the mole and how that relates to those masses we just talked about. So you've probably all heard of the mole before in other chemistry courses, and the important thing to keep in mind is that a mole is just a counting word. All right, it's nothing more than that. It's just a collection of atoms. So if we had, a dozen of anything, a dozen eggs, a dozen atoms, a dozen, roses, that's going to be 12. If we had a gross, it's not as common of a counting number, but that's another counting number that you can have. That would be 12 dozen. And if you have a score of something, remember Abraham Lincoln's famous speech, 467 years ago, that meant 87 years ago, so a score is going to be 20. So these are just counting numbers that say, if I have a dozen or a gross or a score or something, that's how many of it I have. In the mole, it's exactly the same type of word. It's just a counting word. But it's a very big number that it represents, 6.022 times 10 to the 23rd. And we can use a mole to really describe anything, although it's such a huge number that, of course, we're going to mostly use it to describe atoms and molecules, which are inherently very tiny. So, we're not going to count people in moles because there's nowhere near 1 mole of people in the world, and we're not going to count, eggs in moles because, again, that's just a stupidly large number. And this number here, this 6.022 times 10 to the 23rd, which is on the periodic table that we use for the exam, is called Avogadro's number. Now, I believe the story goes that Avogadro didn't even come up with this number. It's just that someone who really admired him, had some sort of man crush on him, named it after him. But he didn't actually come up with this. I don't know who's responsible for this. But we'll talk about Avogadro's contributions later on in the course. He is a very important scientist. He deserves to have something named after him. And this number is that thing at the moment. So it's a very important number for us, and it represents the number of things in 1 mole. So it's kind of fun to wrap our head around how big a mole is. I told you this is a huge number. We're going to use it for counting atoms and molecules, but what if we counted regular things with moles? So let's say that we had a stack of 1 mole of M&Ms, and we're going to lay those M&Ms out over the entire United States of America. So basically we're going to lay them out in one layer all next to each other, and then we're going to keep stacking them until we've used up 1 mole of M&Ms. So we can estimate how big of a layer we're going to make. So let's assume that the volume of 1 M&M is around 1 cubic centimeter. That might be a slight overestimate, but it's fine for us. The area of the USA, I don't know if this counts Alaska or not. I'm not sure where I got this number, whether it's 48 contiguous or Alaska. But anyway, it's 3.02 times 10 to the 6 square miles. So I'm not going to go through this math in detail, but basically what you can do is using the area of the United States and the volume of M&M, you can figure out if I had 1 mole of M&Ms all stacked up on top of each other, how high would that stack be if it covered the entire United States of America? And that height, anybody want to wager a guess? No, so how high would the stack of M&Ms be? If I were to take 1 mole of M&Ms, stack them up covering the entire United States of America, how high would it be? Keep in mind, so the United States is big, M&Ms are small, so how high would the stack be? There's no wrong answer, I'm just seeing what anybody thinks. 3 feet. All right, that's a good guess, but you're off by a couple orders of magnitude. It's 50 miles. So that's how big a mole is. If we had 1 mole of M&Ms, it would make a 50-mile tall stack if we covered the entire United States. So it's a huge, it's a number that we can't even really comprehend on the human, length scale. It would constitute 8 million layers, basically. All right, so we'd have to stack M&Ms over the United States 8 million times all on top of each other before we finally used up 1 mole of M&Ms. Or another thing we can think about is how many teaspoons of water are there in all of the world's oceans? So let's say we wanted to scoop out all the water from the ocean, 1 teaspoon at a time. How many teaspoons would that be? So the volume of the oceans is approximately 1.3 times 10 to the 9th cubic kilometers. So that's how much water is in the ocean. Which corresponds, if we convert that into teaspoons, that's going to be about 2.65 times 10 to the 23rd teaspoons, which is around 1 mole. All right, so basically all the teaspoons of water in the entire world equal about 1 mole of teaspoons. So again, that should hopefully convince you that this is an absolutely huge number. All right, think of how many times you'd have to scoop out a teaspoon of water before you went through all the water in the world. So the mole is a huge number, but like I said, we're going to use it to represent collections of very, very tiny things like atoms and molecules, and that's why it's very convenient to use in chemistry. Now, obviously, we can't practically go in and count out a mole of atoms or a mole of molecules. There's no, as I said, it's such a huge number, and atoms are so tiny. How would we do that? So what we're going to really be focusing on in this course are certain key relationships that involve the mole, because the mole is going to be a very useful quantity for us when we start talking about chemical reactions, and we want to know how does the mole relate to other measurable quantities, things that we can measure in a lab. So the first one is the relationship between atomic mass and moles, which is a very important one. So we gave you the atomic mass. We defined it in AMUs, where AMUs is going to be 1/12 the mass of a carbon-12 nucleus. But it also has a very important relationship to moles. So the atomic mass represents the mass in grams of 1 mole. So there are really two ways to interpret atomic mass. And this is going to be the one that's even more important for us in this course. So if we have exactly 1 mole of an element, the mass of that is going to be equal to the atomic mass in grams. So the atomic mass for carbon is 12.011, which means that if we had 1 mole of carbon, it would be 12.011 grams, which is maybe a small handful, not a huge amount, as it turns out, because again, atoms and molecules are very tiny. Okay, so that's going to be the interpretation of atomic mass that's going to be most important for us. We can use the AMUs to define individual isotope masses, but what's more relevant is the atomic mass in grams per mole. So with this, we now have 2 conversion factors involving the mole, 2 ways to relate the mole to other quantities. So one is Avogadro's number tells us that there are 6.022 times 10 to the 23rd atoms or molecules or whatever makes up that substance in 1 mole. And then another conversion factor is that the atomic mass of an element in grams per 1 mole. All right? So again, as we go forward in Chapter 5 and beyond, we're going to learn a lot of different relationships involving moles, and these are the first 2. And most of what we're going to be doing, if you want to get really good at the problems we're going to be doing, is going to be converting from one quantity into another. Mass into moles, moles into mass, or other things that involve moles, as we'll see later on. So we're going to start using these conversion factors involving moles for a lot of the problems that we do. So this is going to be the first one that we'll talk about. All right, so let's look at just a few sample problems. So as we get to this part of the course, more problem-based, more quantitative-based, I'll be tending to do a lot more sample problems because those are often the best ways to learn the different ways that we can ask you these questions and the different techniques and methods you have to use to solve them. So let's say we have a helium cylinder. So if you go to a party store and they're blowing up balloons with helium, they might have one of these. And let's say that it has 239 moles of helium. How many helium atoms are in the cylinder? All right, so again, when we want to think about the relationships that we have involving moles, and if we're looking for the individual number of atoms, the number of individual atoms, or the number of individual molecules, we should automatically think of Avogadro's number. All right? So we want to solve for the number of helium atoms. And we're going to start using what's called the factor label method to do these problems. We're going to use conversion factors to go from one quantity into another and make sure that the units that we want are left at the end. So if we start with 239 moles of helium, we know that Avogadro's number tells us that there are 6.022 times 10 to the 23rd atoms of helium per 1 mole. So we're going to use that as a conversion factor. So there's that many helium atoms in 1 mole. And I think it's very important to write out units when you're doing these types of problems especially. When I've helped other students in the past learn how to solve problems like this, Most times when people are making a mistake, it's because they're either not writing the units at all, thinking they can take a shortcut, or they're writing the wrong units out and they don't quite have it together what it means. So write out the units, know what they mean. So what we see here is that moles of helium cancel out, they divide out, and we've now converted moles into individual atoms. So if you know the definitions of these conversion factors and the units that they apply to, you can arrange them in the correct way to get you from one quantity into another. And so when we multiply this out, we get 1.44 times 10 to the 26 atoms. All right, so that's a very straightforward one-step conversion from moles into number of atoms. And again, this is one that you'll certainly see it on the homework and the test. It's not one that we use a lot in real chemistry research because, like I said, we're not going to be really counting individual atoms or interested in how many individual atoms we have in most cases. But this is one conversion we can use. And so the key point for this problem is that when you're counting atoms and molecules, when you want to know how many individual atoms or molecules there are, you just have to use Avogadro's number. Because Avogadro's number applies to any substance in the world. The identity of the substance doesn't matter if you just want to know how many atoms or molecules there are. If you're just taking moles and converting it into atoms or molecules. So in other words, I set up this problem as, this is a cylinder of helium. We set up the problem this way to find out the number of helium atoms. But if I had told you it was a cylinder of argon or a cylinder of neon or a cylinder of xenon, any other gas or any other element, you would set it up exactly the same way. So it doesn't matter that this is helium, you still use the same Avogadro's number and nothing changes about how you do the calculation. Avogadro's number applies to 1 mole of any substance, 1 mole of any element, or 1 mole of any compound, as we'll talk more about next week. All right, so let's do then a slightly different example. All right, so some people that are worried about the stability of their local currency invest in gold. So if you have an American Gold Eagle bullion coin, it contains 31.1 grams of pure gold, and we want to know how many moles of gold are in the coin. All right, so again, this is a pretty straightforward conversion, but this time we're given the mass of a substance, so we have to use the mass of an element. We have to use its atomic mass to convert between grams and moles. So look at the given information in the problem. That's often going to be your first clue to which of these conversion factors am I going to use. So the moles of gold is what we're interested in. So when we set up these problems, again, look for what the question is asking us. It's looking for how many moles of gold. So that's what we're solving for. And we're going to then do conversions until we get into that proper unit. So the given quantity is 31.1 grams. And remember that the relationship between grams and moles is going to be the atomic mass. But the question is, do we multiply or do we divide by the atomic mass? And that's where looking at the units is going to tell you automatically what you have to do. So we're trying to cancel out grams and convert into moles. And so remember that atomic mass is grams per mole, so we're going to put the atomic mass here in the denominator. So if we go find the atomic mass of gold on the periodic table, atomic number 79, and the atomic mass is 196.97. It's that number below the atomic symbol. All right, so there are 196.97 grams in 1 mole. So that's what the atomic mass tells us. And we're going to write it in this way so that grams cancel out and we convert into moles, which is the desired quantity. So as soon as we've converted into our desired quantity, we stop. So again, this is only a one-step problem here. And we get 0.158 moles. All right, so mass into moles is going to be a conversion that we are going to do hundreds, thousands of times in this course. So this is sort of our first introduction to it. It's one that we're going to see a lot as we go forward. All right, so then the important key point for this type of problem is when converting mass to moles, you need to know the identity of the substance because you need to know its atomic mass. All right, so we set up this problem with the atomic mass of gold, but if it was some other substance, we would need to use the appropriate atomic mass. So unlike Avogadro's number, every substance has a different atomic mass, and you have to make sure you use the correct one when you're converting from mass into moles. Okay, so that's the difference here with this one. All right, and then finally we'll end up with a couple of multi-step problems here. So those were both one step, converting either number of atoms into moles or vice versa, or converting mass into moles or vice versa. Now let's look at some that have a little bit more involved with a setup. All right, so we have a recently discovered nanoparticle. So it's a particle that's on the order of a few nanometers, in this case 1.3 nanometers, was determined to have 37 indium atoms. So one of my former classmates was one that sort of discovered this, and they found that there are 37 indium atoms in the structure. What is the mass of indium in grams for one particle, in one of these particles? All right, so we're going to try to figure out, okay, if we have 37 atoms of indium, what is the mass in grams for those 37 atoms? Now we can imagine it's going to be a very small number because 37 atoms is a very small number of atoms, but let's see how we do this conversion. So we're looking for the grams of indium. So again, we're going to do conversions until our units wind up in grams of indium. The given information, we have two pieces of given information, the diameter of the particle and the number of indium atoms. Now, do we really care about what the diameter is if we're just trying to count or measure the mass of indium? Well, no, we don't. So this is irrelevant information, but the number of indium atoms is what we're going to start with. So we have 37 of those. And the first thing we can do, if we have the number of atoms, we can convert into moles using Avogadro's number. All right, so we convert into moles first. We're going to divide by Avogadro's number in this case. And again, that's going to cancel out atoms and convert into moles. But the problem asks for grams of indium, so we have to do one more step. And now that we know the moles of indium, we can convert in the next step into grams by using the atomic mass. So the atomic mass of indium, I'll have to go find it. It's right here, number 49, 114.82. So that's the atomic mass of indium in grams per mole. So we want moles of indium to cancel. We want to convert into grams, so we're going to put the atomic mass in the numerator. And that's going to be the grams per 1 mole. So moles cancel out. We've now gotten to our desired quantity, which is grams, and so we just multiply the things across, and we get 7.05 times 10 to the minus 21st grams. So again, a very tiny quantity because there's only 37 individual atoms. All right, so again, for these types of problems, writing out the units is going to be crucial. If you prefer to do it in 2 individual steps, that's fine. You could have done one step where you converted atoms into moles, and then a second step where you converted atoms into grams, but I prefer to just sort of do it in one string of conversion factors, where as long as you write out the units, you'll always know whether you put it in the numerator or the denominator, and you'll always know when to stop because you're going to get to the units that you're looking for. All right, so then finally, before I let you go for the weekend, one last example, talking about, again, our favorite element to hoard, which is gold. So a gold bar weighs 12.4 kilograms. So if you're really wealthy, you can get a whole bar of gold, not just a coin. And we want to know how many gold atoms are present in a gold bar. All right, so we want to know what's the individual number of atoms. All right, so again, we're given a mass, and this time in kilograms. We don't have a direct conversion from mass into number of atoms, but we can do this in a stepwise process. So the number of gold atoms, we're starting with 12.4 kilograms of gold. That's the quantity that we're trying to convert. Now we should recognize, again, importance of units here, that the atomic mass is going to be grams per moles. So if our mass is not in grams, we cannot immediately convert it into moles. We have to get it into grams first. So the conversion from kilograms into grams is going to be the first thing we do. So if we want kilograms in the denominator, there's going to be 1,000 grams per 1 kilogram. Or you could write it as 1 gram per 10 to the minus 3 kilograms, however you prefer to think about that. But again, kilo means 1,000, so there's 1,000 grams per kilogram. And now we can convert into moles. So again, we're looking for the number of gold atoms, so we have to get into moles first. We don't have a direct conversion from grams into number of atoms. So it's going to be 1 mole of gold per, again, the atomic mass of gold, 196.97 grams. All right, so grams of gold cancel out. We've converted grams into moles. But again, the problem looks for individual gold atoms, so we have to do one more step, which is Avogadro's number. So we want moles to cancel out. and then we're going to convert into atoms. And so there are 6.022 times 10 to the 23rd atoms in 1 mole. So moles cancel out. We've now converted into atoms of gold, and so we get a pretty large number here, 3.79 times 10 to the 25th atoms. All right, so really the key to doing these problems is to know the value conversions that you can do, make sure that you keep track of units all the way across, and just practice them over and over again to get the hang of them. All right, I'll see you Monday where we'll start talking more about chemical reactions.